In this video, we're going to do some calculations with weak acids and weak bases. In the previous video, we saw strong acid, strong base calculations, and now we're going to have to take a look at something a little bit different because remember that weak acids and weak bases do not ionize 100%. These relationships will still apply in a similar way that we saw before, these ones here in particular and this one. What might be a little bit different is this relationship here. I might employ this a bit more than we did previously because Kas and Kbs apply to weak acids, weak bases, not strong acids, strong bases. So we're going to talk about a concept called percent ionization, and it's basically the percentage of a solute that ionizes when you dissolve it in a solvent. That really refers to the idea that acids and bases that are weak do not ionize 100% in solution. So for strong acids and strong bases, percent ionization is 100%. It goes to completion. That's why we could have said things like the concentration of H3O plus is simply the concentration of your strong acid, or the concentration of your OH minus is the concentration of your strong base times whatever molar coefficient it has when it dissolves, right? If it's a 2-to-1 ratio for your base versus your hydroxide ions. But for weak acids and weak bases, the ionization is only partial. It's less than 100%, and so that's why there's actually a reversible reaction that happens and it could reach equilibrium eventually. And the equilibrium favors the left side. So in other words, very little of the acid and base gets ionized when you're weak acid, weak base. So you can actually figure out the percent ionization, what percentage of the acid will convert into the conjugate base. So the version like this is the acid, this is the conjugate base. You can do that by essentially just doing ionized divided by initial times 100%. So you can do ionized, so this is the ionized one, the conjugate base, over the acid times 100%. Sometimes you might see it written as Cb over weak acid times 100%, and that's the same thing. And that would be called the percent ionization. That's the percentage of the acid that has become the ionized version. You can do the same thing for weak bases. So you just do the ionized over initial times 100%. If you want to write it more with respect to the acids and bases, you can do the conjugate acid divided by the weak base times 100%. So you might sometimes see conjugate acid divided by weak base times 100%. And so what we're going to do is we're going to do this practice problem here together. We're going to figure out what the pH of a solution of HClO is, and we're going to determine the pH, the percent ionization after that. So to do this, we have to recognize this is a weak acid. So we're going to, knowing that, we're going to write out the equation for the weak acid ionizing in water. We're going to make our reversible reaction here, and that's going to give us ClO minus AQ plus H3O plus. And to find the pH, we really just need to know what the concentration of H3O plus here. So it's not different than finding the pH for a strong acid in that respect. You still need to know the H3O plus. The difference is how do you find it? Because for the strong acid, you could just take the concentration of the strong acid and make it the concentration of H3O plus. But for a weak acid, you can't because the percent ionization is not 100%. So you will have to make an ICE table, and you'll actually have to use a Ka value to solve for X. And the Ka value is given to you here, but if you don't have it given to you, you can go in your tables provided to you and you can find the Ka. We're told that the concentration here is 0.64 molar. We don't need water because it's not going to be in our equilibrium expression. Initially, you'd have 0 this, 0 this. That's minus x. This is plus x. And then this is 0.64 minus x. This is simply x, and this is x. And so you can write an equilibrium expression. You can write that Ka is equal to the concentration of ClO minus times the concentration of H3O plus over the concentration of HClO. So now you can plug these values in. You can see that 2.9 times 10 to the negative 8 is equal to x times x, so x squared, over 0.64 minus x. Now you could check the 100 rule to see if it's going to work, and it might actually work in this situation. It's not a very hard one to solve for. You will have a quadratic, but we can try the 100 rule out. So let's just test it out. 100 rule. The initial concentration was 0.64 over the Ka. I'll just put Ka here, but you know that the Ka is up here. And if you have some math sense, you'll see that when you're doing 0.64 divided by such a small number, you know it's going to be much greater than 100. So 0.64 divided by 2.9 times 10 to the power of -8, and you get a very big number that's much greater than 100. So I don't have to write that down, but the number is much greater than 100. Therefore, we can make the 100 rule assumption. We can do that. So we can take this part out. And now essentially, we're just solving for x by doing 2.9 times 10 to the power of -8 times 0.64. And I'm going to square root that to get x. And that will be the concentration of H3O+. And it's also going to be the concentration of our ClO-, right? Because it's the same thing, it's x there as well. So we'll do 2.9 times 10 to the power of -8 times 0.64. We'll square root our answer here, and we'll get about 1.36 times 10 to the power of -4 molar. So there's sort of two parts for our question. Let's call this part A. We want to find the pH. So pH is negative log of the concentration of H plus or H3O+, which you just found. I'm not going to rewrite it. I'm just going to show you I'm putting it in here. So we'll do log of this answer, and we'll get that the pH is about 3.865, or approximately, let's see how many sig figs we need to round the to 2 sig figs. So we can say 3.9. Now, the next parts of the question was a percent ionization. So the percent ionization is going to be equal to the concentration of the conjugate base, which is ClO- at equilibrium, over our initial concentration, 0.64. So let's go over our concentration of HClO, but the initial one, times 100%. And so we found our x value, which is the concentration of ClO-. So we have 1.36 times 10 to the power of -4 molar divided by the 0.64 molar times 100%. And you'll see it's a very small percentage, 1.36 times 10 to the power of -4 divided by 0.64 times 100, and you get that this ionization is about 0.021%, or you could say 2.1 times 10 to the power of -2%. So a very small percentage of this acid actually ionizes into H+, which again supports the idea that we do have a very weak acid here. The Ka was very small, so we know that the reactants are favored, which means that essentially this side here is favored, so you have more of this unionized acid compared to this side here. So you're not going to get a lot of ions form, which is why this may not conduct electricity as much as let's say a strong acid might. So make sure you can do this problem. The other videos are essentially solving other problems similar to this one, including weak acids and weak bases in some more detail.